Welcome to lecture number 7, and this talk will introduce you to a concept known as a basis set. What is a basis set? It is a set of mathematics that is used to start a computational chemistry calculation. And what you're going to learn in this session and in the following session is about the variety of different types of basis sets that exist. And there are some different types. If we're doing a Hartree-Fock calculation, otherwise known as ab initio, or self-consistent field theory, there are a variety of types of basis sets. The first type is called a minimal basis set, and that's what we'll focus on in this discussion. Then there are also split valence. We'll take those up in basis sets part 2. Polarized and diffuse. These are all the basic types of basis sets that are found in the most general Hartree-Fock methodologies. There are also some higher order basis sets that we'll talk about in some detail in the next section, but I'll introduce them here. The first type are called Mollier-Plesset, otherwise known as MPX, and the X there is going to be a number like MP2 or MP4. Okay. There is also what's known as a full configuration interaction, or CI types of basis sets, and we'll talk about those a little bit next time. And what you're going to see is that basis sets represent a series of numbers that you obtain from one or more online databases. And here you see, and this is a little slightly older picture of the Gaussian basis set order form page. And what you should see here in the top box there is that there are lots and lots of different types of basis sets. If I was able to scroll here, I'd be able to show you several hundred different basis sets. And no, you don't have to learn all those different types, but you do need to be able to have an understanding of what type of basis sets they are and what they might be able to do for you. Okay, so let's get into this a little bit. Here's a chart that you're going to see several times, and I'll introduce it here. At this stage, what you need to understand is in the bottom right-hand corner, if you look down the bottom right-hand corner, you see a box there that says Schrodinger's Equation. And what that means is being able to solve Schrodinger's equation exactly and get exactly the right answer for that equation. You should understand by now that with the current state of the art and the technology, that's not possible. But we can get pretty close to that. And the way we get close to that is coming down the left-hand side of the chart, you see the label basis set types. And you see where I have listed minimal, split valence, polarized, diffuse, high angular momentum, or moment. All the way down, there's a dot, dot, dot in between there going down the left, down to infinity, where the basis set is of an infinite size. The shading that I have there, notice that that shading is under a category going across the top of the chart there, and it's labeled electron correlation. We have not talked about electron correlation yet, but fundamentally the HF or Hartree-Fock method does not have any electron correlation, and we'll talk about that in subsequent discussions. So what this chart is trying to tell you is as I come down the chart on the left-hand side, meaning from top to bottom, and I improve the size and quality of my basis set, and as I go across the chart from left to right and improve my correlation, you see on the far right there it says full configuration interaction, that if I'm able to do both those things, have a infinitely big basis set and full configuration interaction, or full CI, full electron correlation, then I'll be able to solve Schrodinger's equation exactly. We're nowhere near close to that at this stage in the state of the art of computational chemistry, but hopefully we will be in a number of years. Okay, this chart sort of shows the same thing, and what I'm trying to show here, if you recall, we've said several times that the Holy Grail in computational chemistry is to find the value of the energy. And really the Holy Grail is to find the lowest energy value. So if you see, take a look at the arrow going up, that's the arrow represents energy, and pointing up means the energy is getting higher or larger, and that's a bad thing. And at the very top of there you see the Hartree-Fock energy. So when you do a typical Hartree-Fock calculation, you're getting that energy value, and it's not very good. Okay, if I come down lower there, you see where it says the Hartree-Fock limit. That's the best energy I could possibly get using the Hartree-Fock method. Coming down a little bit is you see the configuration energy. That's an improvement. So as I go down the energy arrow there, as I'm getting towards the bottom of the piece of paper, that means the energy values are getting more accurate. And you see the next to the last one is the exact solution of what's called the non-relativistic Schrodinger equation. That's full CI. And at the very, very best, we could get what's called relativistic energy. We might talk about that later on in the course. What you should see between the difference between the Hartree-Fock limit and the exact solution of the Schrodinger equation is this thing called electron correlation energy, and we will talk about that more in depth later on. At this stage of the game, you need to understand that when you do a Hartree-Fock calculation, you're really not getting a very good answer as compared to what the right answer should be. But the good news is your answer is good enough for you to say something intelligent about the chemistry you're trying to do. All right, let's talk now about some basis set stuff. And again, there are these categories of minimal, something also called double zeta, something called split valence, called polarized, diffuse, and we'll talk about the double zeta, split valence, polarized, and diffuse basis sets in the next lecture. Okay, the basic mathematics here of the base is what's called a basis function. Is this equation n times e, which is an exponential function, all to the value raised to the power of alpha times r. And I hope by now you're beginning to understand that r is the radius in angstroms, meaning the distance the electron is away from the nucleus. If r equals 0, that means the electron and the nucleus are right up against each other. If the radius is 1 angstrom, that means that the electron is 1 angstrom away from the nucleus. Okay. Now, the n there represents something called a normalization constant. And when we normalize something, that means we multiply the mathematics by this normalization constant called n, and that ensures that our function, whatever it is we're trying to compute, adds up to 1. Because again, if you think about what we're doing here, we're trying to determine the probability of finding the electron somewhere in the atom. And there should be a 100% chance that the electron is in the atom, okay? Assuming it hasn't ionized and gone off somewhere else, okay? So the normalization constant there is trying to make sure that the basis function will equal to 100% or 1, okay? So normalization means multiplying, it's a fudge factor, we multiply an equation by that to ensure that it has a maximum value of 1. Okay, you notice a value there called alpha. That's called the orbital exponent, and that's going to be very important in basis sets, and we'll talk about that here momentarily. So the basic mathematics for what's called a basis function is this value, normalization constant times the exponential of minus alpha times r. And what you're going to find out here in this lecture is that the basis set represents a series of numbers that you're going to plug into this basis function. And we'll get into that here momentarily. Okay, assuming before we even start talking about what these basis set numbers are, where do we get them? As I mentioned earlier, we get them from an online database. If you do a Google search on basis set order form, you will come up with this address. Notice, by the way, the address is HTTPS, not HTTP, so be careful about that. But just do a Google search and find the EMSL basis set exchange. This is out of the Department of Energy Labs, and this has all of your information. And we'll talk about how to use this basis set order form in this lecture a little bit, okay? All right, and here's a sample basis set. This is for the hydrogen molecule. You're going to become very familiar with this basis set in this lecture and the lab that accompanies this. For now, what you should notice is all the references. Notice some of the names up there: Warren Henry, H-E-H-R-E, J.A. Popel or John Popel. You'll see that name again momentarily. So these are the people who came up with these numbers. And again, the numbers you're looking at is what's called the basis set. They simply are a set of numbers, hence the name basis set, that you are going to plug into the basis function, and that's going to help you start your calculation in computational chemistry. Okay? And you see a series of numbers down there, and we're going to talk about what those numbers mean here momentarily. Okay, here's another a little bit more complicated basis set, so you see a few more numbers. The first one I showed you a minute ago was the basis set for carbon. This is the for hydrogen. This is the basis set for carbon. And as you might suspect, because carbon is a little bigger atom than hydrogen is, there are a few more numbers in there, and we'll talk about what these mean momentarily. Okay, basis sets. Okay, the primary type of basis function. Okay, be careful your my terminology there. The basic type of a basis function is what's known as a Slater type orbital, or STO. And this contains a variable called zeta, and represented by that sort of squiggly thing there, the Greek symbol zeta. Okay, now you see the basis function over on the right-hand side, and I called it STO for Slater type orbital. Notice that it depends on or is a function of r, the radius. Okay, now where's the normalization constant? The normalization constant is that zeta thing, that squiggly thing raised to the power of 3 divided by pi, all that raised to the 1/2 power, which is the same as saying take the square root of it. Okay, so zeta cubed divided by pi, all raised to the 0.5 power, is the normalization constant. Then you have your e, your exponential, raised to the power of minus zeta times your r value. And that's called the STO function, or more commonly it's called the Slater type orbital. Okay? All right? And this is, as I mentioned, a function that changes as the radius changes. So we start out r being equal to 0, and typically we'll go to something like r equals 4 angstroms or so. That's a typical distance to go away. So as the radius gets bigger, remember the electron is getting farther away from the nucleus, and we're interested in seeing what does that energy look like as we do that. Okay, here's a problem. Slater type orbitals don't work very well with atoms or molecules that have more than one electron, which is a really bad thing, because the only atom that has one electron is hydrogen, and it gets pretty boring just studying hydrogen all the time. So because of the complicated calculus that the computational chemistry server is doing for you, that's the good news. It does calculus for you. You don't have to know how. It does all these calculations, but the Slater type orbitals don't work very well when you get more than 1 or 2 or 3 electrons, and that's a real problem, because the Slater type orbital is the basis function that we want to be able to use in our calculations. So it's basically the best approximation to the right answer that we have. The problem is the computer math, the computational part of the calculation, doesn't work very well. And so we need a solution to that, and as is typically the case in computational chemistry, and I hope you're getting this idea by now, we have to come up with an approximation. We have to come up with some way of approximating or trying to simulate an STO orbital, okay, a Slater type orbital, so that we get as good an answer as we can possibly get, at the same time making sure the math gets done in a reasonable amount of time. Okay, and the way we do that is we use what's called a GTO approximation, and GTO stands for a Gaussian type orbital. And you see it has a very similar structure to an STO function, and instead of a zeta value, we have a value called alpha. It looks like the letter A. So what you should see here is GTO is also a function of r, or radius. The normalization constant here is 2 times alpha divided by pi, all raised to the 0.75 power. And then in the exponential, you notice that that's minus the alpha value times r. Now, the difference here is that the radius r is now squared, okay? And you might think that that's harder mathematics, but it turns out that when you square the R value, that significantly simplifies the mathematics that the computer has to do. Basically, it gets rid of all the negative values. If you think about what if you have some negative values, you simply square it, and then everything is now positive. So squaring that R value there significantly simplifies the mathematics and allows you to model atoms and molecules that have more than one electron, which is everything above hydrogen. Okay. Here's the problem, though. A GTO, a Gaussian type orbital, doesn't give us a very good answer. Okay? It's not a very accurate representation of what's actually happening in the atom or molecule. So the good news is doing it this way makes the math a lot easier. The bad news is we don't get a very good answer. So let's try to give you a picture of what this looks like. Okay, so here's a Slater type orbital. I've solved the function. I solved the basis function for Slater type orbital. That's what you're going to do in your lab, by the way. And I'm solving this Slater type orbital for one electron, and that's for hydrogen, and I'm doing it in one dimension, just in the x dimension. So I'm not worried about three-dimensional XYZ here. I'm just doing it for one direction. And what you should notice here is that the probability of the electron being near the nucleus for one atom, one electron in one dimension is slightly under 80% or 0.8. So you notice there that the Slater type orbital says the electron probably wants to be pretty close to the nucleus. And I recognize this is a little different result than you got in the last lab where you did the hydrogenic orbitals, but keep in mind we're not multiplying any of this times the 4 pi R squared business. We're not squaring anything. So this is a pretty simplistic view. Anyway, regardless, and what you should notice as well is as the electron gets farther away from the nucleus, what happens to the basis function? It gets smaller and smaller and smaller, and eventually as we get to 2 angstroms, 2.5 angstroms, 3 angstroms, 3.5 angstroms, basically the basis function has gone to 0 and is basically doesn't exist anymore. So the Slater type, what we're doing here is we're saying this is a correct answer. This is what we should be seeing for one electron in one dimension, a graph like this. Okay? But again, as I mentioned, the problem is that you can't, the math of this gets pretty hard once you get more than one electron and once you get more than one dimension. Okay? So how do we approximate that? Well, we try to replace the Slater type orbital with a Gaussian type orbital. So I did that experiment, and you will too. So the red line here on this graph represents my plot of the Gaussian type orbital, the GTO, and the green line there represents the Slater type orbital, or the STO. Now, let's look at these two lines. If we're assuming, and you should for this lecture, you should assume that the Slater type orbital is the correct answer. That's what I should be getting for one electron in one dimension. Well, if you look at, okay, if I'm trying to replace that Slater type orbital with a Gaussian type orbital, look at where that red line is. It's nowhere close to 80% or 0.8. It's somewhere about 0.38 or 0.37 or so. There's a huge gap between what I should have at 0.79, 0.8 and what I'm getting at 0.37, 0.38. Okay, that's just too much of a wrong answer. Okay, I got that answer really quickly. Okay, the computer was able to calculate that easily, but it's a really bad answer. So what you should be getting out of this slide is this Gaussian type approximation just doesn't do a very good job of giving you a good answer if I'm trying to replace the Slater type orbital with a GTO approximation. Okay, so how are we going to get around this? How are we going to resolve this problem? Okay, well, we're going to use a little trick. We're going to use multiple GTO orbitals. And the good news is you're going to be able to do the math by yourself, because what we're going to do is we're simply going to calculate some number of GTOs, 2, 3, 4, 5, or 6, and we're simply going to add them together. Okay? So, for example, I'm going to approximate a Slater type orbital, in this case by calculating 3 separate Gaussian type orbitals. And I'm going to call them Gaussian type orbital 1, Gaussian type orbital 2, Gaussian type orbital 3. I could keep on going. I could do 4, 5, 6. Usually we don't go any higher than 6, but I could. Okay. And what you should notice, by the way, is I have a little coefficient in front of each of the GTOs, A, B, C. And the A, B, C represent, these are constants, and they are different numbers. And they are known as contraction coefficients. And it would be good of you to know what this term, you should know what this term is and what it means and where you get this term. Okay, so to approximate an STO, instead of just using one Gaussian type orbital, I'm going to take a couple of them. I'm going to add them together, but before I add them together, I'm going to multiply them by this constant called a contraction coefficient. Okay, and now you're going to have what's called a new basis set, and this is called an STO-NG, okay, basis set, where N is the number of GTOs that you added, okay. And for example, in an STO3G, oops, let me go back one. I'm sorry I didn't go so fast. In example STO3G, I'm going to have GTO1 plus GTO2 plus GTO3. And the G there represents the, is shorthand for Gaussian type orbital. So what the STO3G notation tells you is I'm going to approximate, or I'm going to simulate an STO orbital by adding together 3 Gaussian type orbitals, okay? And that's what you're going to try to do in the lab for this particular week. All right, so when I do that, okay, and you will try to reproduce this graph yourself, okay, when I try to do that, I have the red line as being the STO function. I plotted that, and that's the red line. The green line is a plot of the STO3G approximation. And notice now I should be getting 0.78, 0.79, or 78, 79%. And now with the STO3G, I'm getting 61%, 0.62 or 62%. That's a lot better than the 38 or 39% I was getting earlier. How might you make this even better? If you did an STO6G, if you took 6 Gaussian type orbitals and added them all together, you would get a much better approximation, and you're invited to try that experiment in the lab for this week. Okay? So let's talk a little bit about STO-NG basis sets. Okay? They are known as minimal basis sets for the reason that they're pretty minimal, and they're also known as Pople basis sets, named after John Pople. And Dr. Pople won the Nobel Prize for his development of these basis sets. He was the first one to develop a basis set, and he was also the developer of the Gaussian software. Okay? They are very poor basis sets. They are very bad ways to begin a computational calculation, and they're very bad for a couple reasons. One of them is that they assume all the electrons in an atom or molecule are identical. So you should know by now you have these inner shell or core electrons, and you have valence shell or outer electrons. And these minimal basis sets assume all of these electrons behave exactly the same way, and in reality they don't. Okay, and we'll have to deal with that in the next unit called basis sets 2. Okay, and this is clearly not true. All electrons are really not created the same. And we would only use a minimal basis set for what's called an exploratory calculation. If you want to get sort of a sense of what some molecule is doing, you would use a minimal basis set. The other place we use them, they're a good choice for educational purposes, and we'll use them with you guys a lot. That's because they run very quickly as compared to the larger basis sets, and they give us a pretty good answer, at least good enough for you to begin to understand what's happening in the chemical system. Okay? You would almost never use those for any kind of serious research. The only reason you would use a minimal basis set in any serious research is if you were comparing a minimal basis set to the larger or higher order basis sets, and it's just a reference point for doing some comparison. Okay, once again, where do you get these numbers for these basis sets? You go to the basis set order form or the basis set exchange. And what I've done here is I've clicked on the word in the periodic table, I've clicked on hydrogen, and I scrolled down in the menu there. It's pretty close to the bottom to where it says STO3G. Under format, I chose Gaussian 94 because that's the format I particularly like the best. And then on the right hand side, you click on the button that says get this basis set or get basis set. You really should make sure you know how to do that. Although I'm doing it for you sort of in this lecture, I'll be giving you the data you need for the lab. Okay, and now here again this is the Slater type orbital 3G basis set for hydrogen. Now, what you should understand is that you are mimicking a Slater type orbital by adding together 3 Gaussians. Okay, and what does a Gaussian type orbital need? It needs a value called alpha. Okay, if you have 3 different Gaussian type orbitals, how many alpha values do you need? You need 3 different alpha values. So coming down to the numbers at the bottom, the very first number there that you should see 2 columns of 3 numbers. That's because I have 3 Gaussians. The very first number there, the 3.425 number, that's the alpha value for Gaussian type orbital number 1. The 0.6239 number is the alpha value for the second Gaussian type orbital, and the 0.1688 number is the alpha value for the third Gaussian type orbital. Okay, going over to the right-hand side, the 0.154 is the contraction coefficient, so you will multiply that contraction coefficient times the Gaussian type orbital calculation. We'll show you that in a minute. So the 0.15 is your contraction coefficient number 1, the 0.53 is your second contraction coefficient, and the 0.44 is your third contraction coefficient. Okay, let's see what that looks like. Now, this slide's going to be very busy. Let me try to walk you through that a little bit. So what this says is to approximate a Slater type orbital with 3 Gaussians, I need 3 separate GTO calculations, GTO1, GTO2, and GTO3. Okay? To calculate GTO1, I need to know the value of the radius, and the alpha value is 3.4252509. Okay? For the second Gaussian type orbital, I need to know the value of the radius with the alpha value of 0.6239. And for the third Gaussian type orbital, I need to know the value of the radius, and the alpha value is 0.16885. Okay? Now, once you do that, that entire GTO number gets multiplied by that contraction coefficient, and I've labeled them CC1, CC2, and CC3. And you see the 0.154, the 0.53, and the 0.44 numbers all being multiplied times the Gaussian. Okay? And I did one sample Gaussian type calculation for you. So basically I went in, I took the 3.425 number, I plugged it in everywhere where I saw an alpha value because that 3.42 number is the alpha value. So 2 times 3.4 divided by pi, all that raised to the 0.75 power. Then the exponential minus 3.425, all times the radius squared. Whatever number I get out of that calculation, I multiply that entire mess by the contraction coefficient, 0.15432, so on and so forth. Okay? And in the lab, and you may use either a spreadsheet or a GNU plot, okay, you're going to do a couple plots. You're going to plot an STO orbital for hydrogen, and you should get exactly the same graph that I got a couple slides ago, that one that goes up to 80% or so. Okay? You should now plot a Slater type orbital 1G orbital for hydrogen just using 1 Gaussian, and I did not show you that in any of my graphs. Okay? You should then plot a Slater type 3G orbital for hydrogen, okay, and I showed you that in a graph. And if you're feeling ambitious, and I would strongly encourage you to do this, is plot a Slater type orbital 6G orbital, and you'll need to calculate 6 different Gaussian type orbitals, multiply each of them times their contraction coefficient, and then add all those numbers together. Okay? It's really going to be important. The reason it's good to do the STO6G is because that will help you make sure you can find the alpha and contraction coefficients numbers yourself. If you stop at STO3G and you're using the numbers I gave you, that's fine, but you better make sure you know where to go to find those numbers. Okay, the second part of the lab is we're interested in trying to figure out what's the effective basis set on how long it takes you to run a job, or what's your CPU runtime. So for 3 different basis sets, STO3G, which you should be able to say something intelligent about now, 321G, which you don't know anything about yet, 631G sub D, how many basis functions are generated. And basis functions are generated from basis sets and are directly correlated to basis set size. Okay, and we'll talk a little bit more about them in the second section. They're also in the reading, they're also in the lab. Okay, but basically you need to understand the bigger the basis set, the more basis functions you will have. So you should understand that STO3G is a very small basis set, at 321G is a bigger one, and 631G sub D is an even bigger one. So what you should be seeing every time you run these is you should be getting more and more basis functions. And as you'll find out in the next lecture, one basis function is correlated to us knowing one atomic orbital. And as we start getting into more molecular orbital theory, this fact will be very useful and very relative. Okay? All right, the test set that you're going to use for the part 2 of the lab is you're going to use the first 10 organic alkenes. So CnH2n plus 2, so methane, ethane, propane, butane, pentane, so on and so forth, up to the first 10, up to decane. So, and if you think about this, you're going to run 10 different molecules 3 different times for 30 total calculations. And we'll talk about getting you into groups for this. That might help as well. And then being able to swap some data, because that's a lot of calculations to do. Okay, any questions, you let me know, and we'll see you online. Thanks very much.